Good afternoon, everyone. I hope you had a pleasant and restful spring break. Welcome back to the Georgia Tech Manufacturing Institute Spring 22 Lunch and Learn Lecture Series. My name is Dr. Billy D. Brown, and I'm a Senior Research Faculty and EWD Director for the Georgia Tech Manufacturing Institute, or GTMI. I'm excited to continue to host this informative series along with our Strategic Partners Director, Ph.D. I encourage you to please spread the word so we can continue to grow our audience and network, which provides value to our community and stakeholders. Before I introduce today's speaker, I will first introduce GTMI, provide some brief instructions for the audience. GTMI is one of 11 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners from moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment located on main campus for basic research and nearby on 14th Street for more applied research in our advanced manufacturing pilot facility. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts a Lunch and Learn series each semester. This spring, sessions will be held Mondays at noon as live online events. These sessions are excellent opportunities for Georgia Tech faculty, undergraduate and graduate level students and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. To ensure a smooth presentation experience, all audience members are automatically muted. If you have questions or comments for the speaker, please use either the chat window or the Q&A panel on your screen. I strongly encourage you to go ahead and submit your questions as soon as you have them so that the speaker can address them promptly at the end of the presentation. Today, I'm pleased to introduce Mr. Matthew Jackson, who will discuss Composites Applications, Manufacturing, and the Vision Forward. Matthew is an Associate Fellow in the Solvay Research and Innovation Organization with a focus on evaluating, developing, and internalizing strategic and emerging technologies. He has been involved in expanding the state-of-the-art in process efficiency, material development, and performance, as well as virtual engineering. In today's session, Matthew will discuss structural composite materials that have a legacy in aerospace applications where the focus has traditionally been on performance. Lightweighting efforts across the transportation industry is putting substantial pressure on the composites manufacturing industry to meet the need for high rate, high volume, and low cost solutions. Matthew will discuss how materials as well as manufacturing technologies and processes must evolve to meet the demands of new markets. Matthew, you may begin your presentation.
Thank you. Thank you for the introduction, and thank you for the opportunity to speak to this group today. As you can see on the title slide, I'm going to be talking about composite manufacturing applications and vision forward. And this is really from the perspective of a material supplier or material developer, because that's what Solvay is. We make and sell composite materials, and so it'll be fairly high level, but we're going to talk a little bit on the manufacturing of composite materials and then how those go into the manufacturing of composite parts. So first, I'm just going to touch briefly on who we are as a company. Who is Solvay? Solvay is really, it's a large global company. We have around 21,000 employees, which span 63 countries, so a pretty big global footprint with about 10 billion in sales. We consider ourselves a science company, but you could also confuse us pretty easily for a chemical company or materials company. And so, we like to think that we develop innovative solutions for customers for sustained shared value. So just to give you an idea of Solvay and the size. And then, what are some of the areas that we're interested in? And so, Solvay as a company, we're interested in aligning ourselves with a lot of the trends that are driving global interest. And so things like electrification, lightweighting, resource efficiency. Solvay in itself has a lot of different material businesses and segments. Today, we're looking at composites specifically. And so when we talk about composites, it's really the top three here that are most aligned with composite materials. And so lightweighting in the material in the center, right? You see the picture of the aircraft. This is primarily where our materials are used for lightweighting of structures for transportation. But you can also think of it for the use in electrification. And so a lot of transport vehicles, whether it's rail or auto or aero, there's a big drive towards electrification. And so our materials, not just composites, but our materials are going towards the development of new, more efficient batteries. But our composites specifically help enable electrification as the weight you add to a structure increases significantly when you add batteries. And so lightweighting becomes really important and actually goes hand in hand with electrification. And then resource efficiency. This is something that's driving our interest and focus as we develop composite materials. How can we develop materials that are more sustainable? How can we develop materials that use less energy to manufacture, and then down the road use less energy in the actual lifespan of the material? So again, the three business segments of Solvay, we have the material segment, which is where we are, the composite materials. We also have the chemical groups and the solution group. So I'm not going to talk about the other two today, but you see it's really about a third, a third, and a third of the different segments. I'm going to talk primarily about the materials group today, which is around 34% of our group EBITDA. Within the materials group, we have our specialty polymers and our composite materials. The focus for Solvay in particular is on high performance. And so for both our specialty polymers and our composite materials, we tend to sit at the top of the performance pyramid. So the top image there shows some of the polymers that we make that are in our specialty polymers portfolios. So these are things like highly aromatic polymers, so things like PEEK and PEC, PPS. And then we also have a wide portfolio of fluorinated polymers and fluorinated materials. So again, specialty polymers, we sit at the top of the performance pyramid. And then with composites, again, I'll get into it a little bit, but composites tend to sit on the top of the performance pyramid when we look at just structural materials. And so those two businesses make up our materials segment for Solvay polymers, or for Solvay materials. I'm going to get into a couple different areas of composite manufacturing today. But I just want to touch on and show that there's, it's manufacturing of composites covers many different areas. And so the first I just talk about here is kind of the one-dimensional product form. And so these are things like the carbon fiber or the reinforcement itself. And then these are things like the polymers and the adhesives that go to hold the carbon fiber together to give it a structure. We also then have the manufacturing of what we call the prepreg. And so the prepreg is an impregnated carbon fiber. And so we take the polymers, we take the resins, and then we combine them in different ways to create this two-dimensional structure that we call prepreg, which then goes to our manufacturers. And then finally, there's the manufacturing of the parts. And so the parts then take a three-dimensional form and tend to carry load. And so there's manufacturing at each stage, right? We have the manufacturing of the individual constituents. We have the manufacturing of the quote-unquote composite, where we bring the constituents together, and then we have the manufacturing of the part. And so the talk today is just going to touch on manufacturing at each of these stages. It's not really a deep dive into any one in particular, but showing how we go from the manufacturing of the constituents all the way to the manufacturing of the part. So again, before we get too far along, did want to just define what a composite is. The word composite is fairly generic. It can mean made up of several different constituents or components. We're interested mostly in an aerospace definition. And so from aerospace, we're talking about a reinforcement fiber combined with a polymer matrix looking to maximize performance. And so in these systems, in these composites, the constituents retain their identities and act together. And so the fiber generally provides the strength and stiffness. It carries the load. And then the polymer matrix holds everything together. This is what allows us to give it shape and dimension, and also helps to transfer the load between the fibers. It also is the primary driver for strength in the Z direction, which is perpendicular to the direction that the fibers run. And so what we see here on the page is a composite cross-section. And so you can see kind of the light areas, which are the individual carbon fiber filaments. And then you see dark areas around that, which is the polymer matrix. And then a little zoomed in kind of cartoon of what we're looking at. And so, each individual filament itself is between 5 and 10 microns, depending on the fiber itself. And they pack together as efficient as possible to create structures that can carry load. And then the polymer matrix basically fills in the space around the fiber. And so carbon fiber was actually first invented in 1879, so a long time ago. But wasn't actually commercialized until 1959. And so when we talk about carbon fiber structures and the legacy and the experience with using these materials as structural materials, it actually isn't that long. So if you compare it to metals, carbon fibers and their composites are relatively new on the scene when we look at them for structural materials. When we talk about a structural composite now, we're talking about how do we actually combine the fiber and resin to maximize performance. So I showed a cross section before. What's really important is to get the ratio of fiber and resin correct. And so ideally, if you want to maximize performance, you want to get as much fiber volume as possible. But a lot of times that comes at the sacrifice of manufacturing and processability. And so we still need to create a system or a structure where we don't have voids, where the polymer can actually infiltrate and help to transfer load and doesn't act as a defect. And so there generally is a balance. And so we tend to target around 50 to 60% volume fraction of carbon fiber to get the best balance of these properties. If you look on the bottom left, it's just kind of a generic stress strain curve of the different constituents. And you can see the fiber, the reinforcement, has really high modulus and really high strength. And the polymer resin, which goes around that, tends to have a much lower modulus and a much lower strength. Ideally, we want to combine these two in a form which can maximize the performance of the structure. And so there's different ways you can do that. We can have the fibers run all in one directional. We call this a unidirectional system. And you see we get strength, a lot of strength in the direction of the fibers, but we tend to be pretty weak in directions that are perpendicular or orthogonal to the fibers. So to overcome this, we start to put fibers and stack them in different directions to get strength in multiple directions. When you do that, though, you tend to sacrifice the overall performance. And so going from that left-hand image to now the right-hand image, you can see running in the X direction, we've actually dropped our strength and dropped our stiffness by putting plies in the transverse direction. So we've increased the transverse direction, but it's come at the sacrifice of the longitudinal direction, and we've increased our shear a little bit. Generally, what we do with composites material is try to get into what we call a quasi-isotropic or isotropic-like material. And so ultimately, we want to try to maximize performance in every direction. And so we do that by having this quasi-isotropic layup. So we have fiber basically in as many directions as possible to give it this quasi-isotropic behavior. And so you see we've again sacrificed our material or our performance in the X direction, but now we've given it strength and stiffness in the X and the Y direction. So when we design an aerospace composite, we tend to take this building block approach. And so if we start with a single lamina, which I show kind of on the left, that's a single layer of unidirectional carbon fiber with the matrix. We then start to build up structures to give it both a Z direction, a dimension, and stiffness and strength in multiple directions. And so again, this gets into some of the nomenclature we use. So we call a single ply with all the fibers running in one direction, a lamina. Once we start to stack these lamina together, we get what we call a laminate. And so in the center, we're showing a 6-ply unidirectional laminate. So again, here we have strength and stiffness really in one direction, the direction of the fibers, but not much in the transverse or shear directions. And so to overcome this, what we tend to do are, again, these quasi-isotropic laminates. And one thing I'll point out is we do try to have a balanced layup. And by balanced, I mean that there's going to be symmetry. And so if you look at the orientation of the plies on the right-hand image, right, we go from 0, minus 45, plus 45 to 90, and then a 90, plus 45, minus 45, and 0. And so we do have a mirror plane in the middle. And that's to try to create as balanced of a layup as possible and to maximize the performance in every direction. So again, the fibers give us directions really in one direction, and we try to balance that out by creating these quasi-isotropic laminates, which then gives us multiple. It gives us strength and stiffness in multiple directions. So again, even here, right, when we vary the layup, we do have the resin still contributing to the behavior in the Z direction. And so a lot of times we're limited by our resin behavior and properties, but we can vary the carbon fiber layup to try to maximize the properties where it's important. This just gives an example of why we would want a layup with different directions. Typically, when we go to these composite structures, we can get away from what we call the quasi-isotropic layup or a balanced layup. And so here, this is just an example of a composite wing skin. You can see that there's these stiffeners that are going kind of from the back of the image to the front of the image. And what you can also see is that the thickness, well, it's maybe hard to see in the image, but the thickness of the composite structure is a lot thicker at the root than it is at the tip. So at the root, we have around 140 plies, and at the tip, we have around 24. And so really the idea is to identify where the loads are, how do the loads travel, and you try to align the carbon fiber such that it follows the load path as best as possible. So a lot of times the actual geometry and the load that the structure is under dictates the layup, dictates the angles, and it dictates the number of plies that we see in a structure. So getting a little more, I guess, into the basics. So, when we talk about a composite structure, again, we're talking about a fiber reinforced polymer, and the fiber is really what gives it its strength and stiffness. And so if you look at different reinforcing fibers, there are a lot that are used. Glass fiber and carbon fiber are two most prevalent, by volume or by mass. When we talk about carbon fibers, we're typically talking about pan-based or polyacrylonitrile-based carbon fibers. And the reason for this is because they give the highest strength and modulus combination and a fairly low density. So if we look at the density compared to glass fiber, our density is quite a bit lower and our strength is quite a bit higher. And so this chart on the right just shows some of the commercial fibers that are available: glass, ceramic, and carbon fibers as well. And you can see carbon fiber really gives the advantage when we're talking about high modulus and high strength. So glass cannot really match the performance. One thing that glass is really good at actually is it's a good balance of mechanical properties and cost. And so for a much lower cost, you can get a really balanced behavior. But if you're talking about ultimate performance, you're really talking about carbon fiber. Within the carbon fiber realm, there are different types of carbon fiber. There's the pan-based, which I just mentioned. Then there's also pitch-based carbon fibers. And you also see a little bit of these kind of rayon and cellulose type fibers. Even within these domains, pan-based carbon fibers make up over 90% of all carbon fibers that are used. And so typically pitch and the rayon and cellulose have niche areas, but for the most part, polyacrylonitrile-based carbon fibers are the bulk of the carbon fiber composites that are used today. When we look at carbon fiber composites, and so we're switching now from just the fiber to the composites themselves, you can start to see that CFRP or carbon fiber reinforced polymers tend to start to set themselves apart of other structural materials. And so when we look at strength normalized by the density, so it's basically, you take into consideration the weight of the structure and the strength, CFRP or composite materials are significantly superior to other types of structural materials. And so this obviously isn't a comprehensive list, but a lot of the materials that you'll see in aerospace, right, things like steel, aluminum, titanium, and even metal matrix composites, CFRP still stands apart from these when you look at structure per weight. And so when we talk about aerospace, that's why composites have really found a home and a start in the aerospace world. But as I'll get into in a few slides, carbon fibers are now being looked at in carbon fiber composites in other markets and other areas for this performance improvement. There's also a right side of the graph here where carbon fiber composites show superiority, and so that's looking at really high temperature systems. And so C/C is a carbon fiber composite that's really been carbonized and graphitized. And so at high temperatures, these materials are unique in that they can retain a pretty high strength at temperatures up to 2,000 degrees Celsius. So applications like hypersonic CC, carbon-carbon materials do show superiority in strength at really high temperature performance. And so carbon fibers, as I said, are haven't been around nearly as long as metals, and you can see that in how big the markets are. And so just, I think, 2 years ago, there was around 93,000 metric tons of composite materials. And if you compare that to steel, which is almost 2 billion metric tons. The use of carbon fiber is significantly smaller than the use of steel and even other types of metals and structural materials. So why are composites used? We talked a little bit about kind of the main pros so far. So the structural performance that you get from these materials is very high, and the weight savings you get. And so the mass per unit, or the strength per mass, or the strength per density, is really the highest of any commercial material that we have now. There's some other advantages too. There's fatigue resistance from these materials that you don't get in metals. And there's a lot of corrosion resistance. And so again, this is why it's found a home mainly in the aerospace world. So things like fatigue and corrosion are really important, and composites offer some inherent advantages there. There are some disadvantages though of composite materials, and they are prevalent. And so one of the big disadvantages is cost. Carbon fiber materials are inherently expensive. And so it's not only the cost of the material itself, but it's also the cost of manufacturing with this material. And so they are quite unique. The manufacturing process is unique and sometimes cumbersome. And so manufacturability becomes a challenge with composite materials as well. Things like repairability is a market that isn't as mature as metals. And so if there is damage, is it something that can be repaired easily and effectively? There's a big area of research right now in the repairability of composites, but it's still considered more or less a disadvantage until the technology matures a little bit further. Electrical performance is another area, and so just by having the polymer matrix around the carbon fiber, we do get a little bit of insulating behavior, and so things like lightning strike protection can become a challenge when you look at using it for structural components on an airplane. And so for the electrical performance, a lot of times to overcome that, we do add metal back into the structure, provide electrical conductivity, which then adds weight, and it doesn't always get us the full benefits of composite materials. And then the last advantage is, for the most part, it's not as sustainable as we would like. A lot of the materials, specifically the carbon fiber, is derived from petroleum. And the way that these composites are made, they're really designed to not break down. And so recyclability, sustainability are some areas that are sometimes considered a disadvantage in an area of active research as well. So if you look at aerospace, again, that's the primary market for these types of materials. And it really has evolved a lot over the last 20, 30, 40 years. And so if you look at the Boeing 767, which was built around 40 years ago, it used only 3% composite materials. The Boeing 787, which was their most recent twin aisle, it's composed of around 50% composites. And so by increasing the composites, we can realize a significant weight savings. And again, this can be improved even further by, one, increasing the number of composite materials on the airplane, and two, optimizing and improving the materials, the composite materials already. So things like making it electrically conductive, so we don't have to add metal back into the structure, will only allow us to realize higher weight savings. So where else are composites used? It really found its home in aerospace, and that's where a lot of this technology was developed. But there's a lot of areas now where it's being explored and applied just because of its advantages in the weight savings and structural performance. And so urban air mobility is one of the most obvious. And so now these are things like air taxis and drones. And so it's vehicles that are small, lightweight, and mobile that fly. And so if you're carrying cargo or if you're carrying people, structural performance and weight is really critical for these structures, especially if they're going to be electrified. And so if we're adding batteries to these structures, which inherently have a lot of weight and mass, composite materials for the structural components makes a lot of sense, and a lot of times is what actually enables this technology to be developed. Wind energy is also another big area. And so as these wind blades get bigger and bigger, the structural requirements for the blades and for the materials themselves become higher and higher. And so a lot of blades have been made with glass fibers in the past, but now as these things get bigger and the loads on them higher, carbon fiber is now being the preferred material for these wind blades. And then finally, rail, right? And so rail has a lot of the same advantages as the other transport mechanisms. Really, you just need less energy if you have less mass. And so a lot of the rail structure now is being explored to be composite, just for energy savings and efficiency reasons. And so at the end of the day, wind still accounts and dominates the carbon fiber usage. That is the biggest market by volume, and it's looking to grow, but some of these other areas are looking to grow substantially in the future as well. So I'm going to talk a little bit now. We're starting to get into the manufacturing, and so I'm going to talk about the manufacturing of the carbon fiber itself because it's the most important component in the composite, because that's what gives it its unique properties. And so I mentioned before, there's a couple different carbon fiber types. There's the pitch, there's the rayon and cellulose. But again, the pan-based makes over 90% of all carbon fiber used. And so I'm just going to walk through the pan-based carbon fiber manufacturing method. It's a fairly complex process. If you've ever had the privilege to walk through a carbon fiber manufacturing line, it's quite impressive how big these are. If you ever get a chance, I'd recommend you take the opportunity to do it. But really, we start by making a polymer. So we start at the simplest stage, even before what I show on the screen here, with acrylonitrile, which is the monomer. We polymerize the acrylonitrile into polyacrylonitrile, and then we dissolve it in a solvent. When we dissolve it, we call this system a dope. So it's a polymer dissolved, and it kind of looks like a honey texture. And at this point, we have really a viscous liquid. We take the viscous liquid and we perform a process we call spinning. And so you basically take the viscous liquid and you force it through tiny holes, tiny little spinnerets, to create fiber that we see here and that we call white fiber. And so once we get to the white fiber stage, we tend to wash out and remove all of the solvent, and we get to just polymer. At this stage, we do start to develop some crystalline structure within the material. We do stretch it to give it some mechanical performance and properties. And this is really what we call, and people refer to as the precursor. After we have the white fiber, it goes through a stage that we refer to as oxidation or stabilization. And so up to this point, we haven't done much chemistry on the polyacrylonitrile, but now we start to do chemistry on the backbone. And so the most important part is the kind of stabilization or oxidation stage. So this allows us to really cross-link the structure, give it some mechanical integrity, but also some thermal integrity. And so ultimately, we want to take it where we drive off the heteroatoms, where we take it to carbonization. But in order to do that, we do have to cross-link the system first so it doesn't melt. And so pan is unique in the sense that the temperature at which these cyclization or cross-linking temperature reactions happen is lower than the melting point. And so a lot of polymers, even polymers with high aromatic content or carbon content, have the fatal flaw of melting before these reactions occur. And so if you have a fiber that you're putting under tension and it melts in your oven, you no longer have a continuous fiber. And so pan is really unique in that sense. And it's why, even though it's been developed around 50 years ago, it's still the primary and prevalent technology used for carbon fiber development today. And so you can start to see some of the color change. The color change is associated with the chemistry we're doing on the structure. So we go from the white fiber to this kind of golden orange fiber, all the way to the black fiber once it's done through the oxidation phase. At the bottom, you can just see some of the structure that we're starting to develop. And so we go from just kind of aligning the crystals within the pan to actually forming cross-links and developing some cyclization, some early cyclization and some latter structure formation in the fiber. The last stage then is to drive it to the carbon fiber. And so we define carbon fiber as having more than 93% carbon. And so on this stage, we're really trying to drive off all of the, or most of the heteroatoms. You see we still have some, we'll have some residual nitrogen and oxygen in the structure, but for the most part, we drive those off as much as possible. The temperature that we go to in the carbonization really dictates how many of those heteroatoms. And so if we want to take that carbon structure to even higher percentages, we take it to a higher temperature. A lot of times that comes at a sacrifice of strength. And so there's really a balance between strength and modulus kind of within this range, 1,000 to 2,000 degrees Celsius. Depending on the carbon fiber that you want, the specific grade, you will heat it to different temperatures and you'll stretch it to different degrees. But at the end of the day, we end up with a structure that has kind of some amorphous content, amorphous carbon content, and some crystalline content. And again, we can vary that ratio depending on the type of properties that we want to try to target. And so the theoretical tensile strength is over 180 gigapascals. So that's if you take just kind of graphite or graphene. But at the end of the day, we don't realize properties even close to that even today. And so the best carbon fibers in the world are around 8 gigapascals in strength, or only 5% of the total performance. And so there's still a lot of room that we can go and grow, and there's still some improvements that can be made in the carbon fiber structure itself. The last step of the process is then doing some chemistry on the surface of the carbon fibers. And so ultimately, we're going to put this within a polymer matrix. And so we want compatibility with whatever polymer matrix we have. And so by knowing what the polymer matrix is going to look like, allows us to dictate what type of chemistry that we do on the surface. And so there's a lot of different ways you can go about this, but electrochemical treatment is probably the most widely used. When you do that, you can target things like oxygen species on the surface, which help compatibilize it with different chemistries. But this is the carbon fiber manufacturing process, kind of in a nutshell, a high-level overview. We start with a polymer dope and go all the way then to a polymer, really a polymer fiber, a carbon fiber that has unique strength and modulus properties. In order to get then into a product form that we can send to our customers, we have to decide what to do with the carbon fiber itself. And so there's two ways that you can really align the carbon fiber. The first I'm going to talk about is the fabric form. And so the fabric form is what most people associate with carbon fiber. So if you looked at something like a carbon fiber hood or a carbon fiber bike, a lot of times this fabric form and geometry is shown off, and that's what people associate with. And so there's some advantages of fabric form. To get the fabric form, we basically take it through a weaving process, typical to what you would see with other fibers and fabrics. But the advantage of the fabric is mostly on the drapeability. And so it allows you to conform the material to fairly complex shapes depending on the part that you want to manufacture. It also has structural efficiency. So just inherently, one ply has fibers running in multiple directions. So there's less of an effort to balance out the fiber direction because it's just inherent in the fabric form. And it's a fairly cost-effective manufacturing process. Part of that is with kind of the efficiency with the fibers running in multiple directions. And so if it is a manual process you're using to make your composite part, there's just fewer plies, fewer layers that you have to lay down. There are some disadvantages with the fabric form though, and the biggest disadvantages is the property knockdown that you see with the fiber. And so inherently, right, each carbon fiber toe is going over other carbon fiber toes in the other direction, which creates this fiber crimp in the structure. And so if you're looking at absolute performance, top level performance, you can imagine as you start to put that crimp under either tensile or compressive load, it's not as structurally sound as a unidirectional fiber, which is really a simple beam, and you do get a knockdown of properties. And so advantages of fabric is really on the the drapeability, the manufacturability, but the disadvantage then is in the overall performance of a fabric composite form. So contrast that with the unidirectional product form. And so this is where the fibers run all in one direction. I talked early on about how we can start to balance the properties, right? So we take these layups and we can rotate the angles of the fibers to give us strength and stiffness in different directions. And so again, the advantages of the unidirectional are the high structural properties. This is where we get the highest performance. But it really comes with the disadvantages of, it's more laborious, more plies are required to get a balanced structure. Again, it takes more work, generally higher cost, which is associated with the higher labor. And then another disadvantage is really the shapes and the geometries that you can conform with the unidirectional. So it does not conform nearly as well as the fabric fiber form. And so this works pretty well if you have a fairly flat panel or geometry. But if you had a curved shape like a radome, something like that, you tend to get wrinkles and crinkles, which then inherently jeopardize the high structural properties that you were going for in the first place. And so each one has its benefits and disadvantages. And so really it dictates on, what is the part that you're trying to make? What is the manufacturing method that you're trying to use? So after the carbon fiber is manufactured, what we look to do is manufacture then what we call the prepreg, or the impregnated carbon fiber form. So again, we can start with either the dry fabric, or we can start with the unidirectional fibers. For the unidirectional fibers, what we end up doing is taking many different toes or spools and lining them up next to each other. And so to create a prepreg, we might have anywhere between 50 to 200 spools that are being unspooled at one time to create a carbon fiber web. We then take those and we spread them out, and then we add a polymer matrix to the fibers directly. And so this can be either a thermoset or thermoplastic matrix. This can be done using hot melt. This can be done using a solvent bath, where we take the polymer of interest, dissolve it in a solvent, and then run the fibers through that. And it can also be done with a slurry process, where we take basically the polymer and we can grind it up and basically deposit particles on the surface, which then get consolidated later. There's many different ways to combine the materials, right? It depends on your input material form, whether it's fabric or unidirectional fiber. Then it depends on the type of polymer that you want to combine it with. At the end of the day, we end up with these prepreg forms, which then go to our customer. And so for Solvay materials, this is kind of our end product, these prepregs, but it is the kind of building block and beginning for the part manufacturers who take the material and then create it into a part. And so the manufacturing of composite parts take the material that I just talked about on the last slide and then begin to conform it to different geometries and dimensions. And so this picture here is showing an automated process where we're taking the carbon fiber, which is the black there kind of highlighted in red, and draping it over a fuselage mold. And so you see here, this is actually done with unidirectional carbon fiber. You see the geometry has a slight contour, but not something so extreme where we would need fabric. And again, in aerospace, a lot of times we're looking for maximum performance, especially if it's something like a fuselage. And so here we take the impregnated carbon fiber. Again, we lay it in different directions depending on the load paths that the material is going to see. We lay it down, or when I say we, our customers lay it down basically in the pre-impregnated form. And so before it's been cured, allow it to conform to the geometry. And then they'll take this and they'll put it into an autoclave or an oven, run it through a temperature pressure cycle to cure and basically set up the geometry. And so composite parts are somewhat unique in the sense that the manufacturing of the part and the materials happen at the same time. So it's not really a composite material until it's cured and the stiffness goes up and it retains its shape. And so we make the part and the material really at the same time. And our job as a material supplier is to provide the material that allows them to do this. So there are some effects of the prepreg manufacturing process on performance. Before I did talk about just the layup, so we can vary the angle of the composite lamina itself to give variety of strength and stiffness in different directions. But when we talk about the manufacturing of the prepreg itself, it can actually create some variability within the microstructure, which has effects on the performance. And so if we take this composite panel, which you see kind of on the top, and we do a side view, again, we're kind of bringing back our polished cross-section, where the little white dots are the individual fiber filaments, and the dark areas are the resin. We can kind of zoom into that area, and we can start to understand the variability. And so depending on the both the prepreg manufacturing and the composite manufacturing, we can get some variability in our microstructure. And that variability leads to changes in performance. And so best case scenario is a completely consistent homogeneous material. But again, that's sometimes hard to achieve. And so again, based on whether we do kind of a melt impregnation, whether we're using unidirectional versus fabric, whether we're using a solvent impregnation, the rates, the temperatures that we use can change the variability that we see within the fiber spacing within the composite. We can also take a top-down look at the same material and get different information. And so, now we're not just looking at the spacing in the direction or the cross-section, but that's the actual distribution of angles that we see from the fibers that are inherent to the manufacturing process. So again, each manufacturing process for the prepreg has a slight different effect on this behavior. But now we're talking about distributions of fiber angles that vary from whatever angle that we want to set it at. And so if we're trying to target a 0-degree ply, the manufacturing method can have up to plus or minus 4-degree distribution of that fiber angle. And so essentially, the manufacturing method, again, can be chosen to try to minimize or expand that. And so a lot of times, if we're looking at low-cost manufacturing, high rate, the trade-off is higher variability. So we get a higher distribution of these fiber angles. So as we deviate more from 0, we tend to get a bigger hit in our properties. If we can kind of go slow and steady, we can reduce this distribution. But a lot of times that comes at the sacrifice of a slower process and ultimately a higher cost material. And so, again, it's all a balance, but manufacturing at different stages of composites can have an effect on the property and behavior. And so one of the things that we can do to try to understand this is start to bring in simulation. And so this is just showing how we can do some coupon simulations where we can take the information that we get in the composite panel cross section, where we can develop a distribution of microstructures. We can take the information that we can get from the distribution of fiber angles. So how did the manufacturing process kind of disrupt us and push us away from this ideal state? And so we can get this rotation of microstructures, and we can start to run these predictive simulations. And so here, what I'm showing is a concurrent multi-scale simulation, or FE2 type simulation, where we develop a distribution of these different microstructures, and then we can systematically vary them to understand the performance that they have on the composite themselves. And so here, right, what we're seeing is basically a tensile coupon, a simulated tensile coupon with different microstructures. And we can see, by varying the angle that we see that's inherent to the manufacturing process, we do see a hit in both the stiffness and the strength. And on the bottom there, on the little plot on the bottom right, then shows some of the cracks and the failure that we start to see that happens prematurely as our fibers become misaligned. And so we can start to understand the effect of the different manufacturing processes and then look to optimize kind of manufacturing rate and cost with overall performance. When we look at the polymer matrix, so we talked about the fiber, we kind of talked about bringing them together in the prepregging process. This is really just getting into the different types of polymer matrix that we can use within a composite. I would say for the most part, thermosets are most widely used. It's around 75% of the market. And so polyester and epoxy are most widely used. Epoxy tends to be for more of the high performance, with polyester being kind of more of the lower cost option. But when we look at thermoset systems, we're looking at melt and solvent impregnation primarily. Again, both unidirectional and fabric form. And these are typically cured by heat, although sometimes we can use an external stimuli or catalyst where we can even get room temperature cure. But for the most part, we'll take our thermoset, we'll impregnate it into our fiber, and then we'll heat it up to set the shape and perform the chemistry. And after the crosslink happens, with a thermoset, you are basically locking into a permanent shape. So looking at the chemistries, these are the chemistries provided by Solvay. These are the chemistries that we work on. And so there is a bigger list out there, but for the most part, this is probably 90%, 95% of all the commercially available systems. So epoxy make up the biggest market. That's what people are familiar with. It has a great performance and a great history. Things like bismaleimide and cyanate esters are fairly unique for high temperatures, as well as polyimides. And then the acrylates and phenolics are more for kind of lower cost industrial applications. So the benefits of thermosets, there's low processing temperatures. They have fairly low viscosity at workable temperatures, so it's easy for impregnation. It's easy for kind of layup in our customers to work and form shapes with them. They tend to have good fiber compatibility, so there's good load transfer between the fiber and thermoset chemistries. And again, the ease of manufacturing, and that's mainly just because of the history working with these types of materials. The other area which is becoming more and more prevalent is thermoplastics. And so thermoplastics have some advantages. One of them is their ability to be softened and reheated, and so the materials can be reused. So after you take it through heat treatment, it's not in a permanent shape. It can be reformed and recycled and reused. And so as far as recyclability, thermoplastics tend to have an advantage there. They also tend to have an advantage on the processing time. And so we don't have to worry about the chemical reactions occurring. Within a thermoset, we have to kind of go slow so we don't get all of the chemical reactions happening at the same time, because it can generate a lot of energy. For a thermoplastic, those have already happened, develop the polymer. And so a lot of times the processing temperature is to take it up above its glass transition temperature, so it's moldable, stamp it into shape, and then cool it down. And so a lot of times the processing time for thermoplastics can be significantly reduced as opposed to thermosets, and that's why there's a lot of promise for these for the industrialization of composites. The other benefit too is high toughness. And so if you just look at a thermoplastic polymer by itself and compare it with a thermoset polymer, the toughness is usually much higher depending on the chemistry. And so you can benefit from some of this toughness that you'll see from thermosets compared to thermosets with the thermoplastic systems. And again, that's one area where thermoplastics seem to have a unique advantage. As far as the impregnation methods, it's mostly the same as the thermosets, although there is this slurry option. So slurry is really where we take the polymer itself, grind it into particles, and then deposit the particles on to the fibers and then consolidate that. And so we can't really do that with thermosets based on the fact that they're in the monomer form, but it works pretty well with thermoplastics. And so it gives us an advantage in that we have a third way to manufacture the thermoplastic composites. When we look at chemistries, again, these are the Solvay chemistries. There are other chemistries that people use, but again, these probably make up the majority of carbon fiber composite thermoplastic systems. So things like peaks and PEX are most common, and then things like PPS and PPA are again getting more into the industrial and automotive phases. So really, the application and design criteria dictate the appropriate matrix. When we talk about designing with composites now, it gets a little more complex. And so what we try to do is replace metal in as many applications as we can. And a lot of times our customers are looking to do the same thing. It gives them weight savings and a lot of times efficiency. And so really, the first iteration, if somebody says, I want to use a composite part or I want to look at replacing metal with composite, the first thing we do is say, well, any current materials work. Is there anything off the shelf that will fit my application right now? If the answer is yes, that's great. If the answer is no, then we kind of go through this iteration cycle again. And so iteration number 2, will small modifications suffice? Is it kind of you need a lower processing temperature to fit into your system, or you need maybe a lower cost, or you need something that's different from a current material, and so you can do some small iterations. And then iteration 3 is really developing a new material. So when we do this, the first thing we go through is the material selection. What do we need to do to solve the problem and fit into the customer's manufacturing process? And then you look at things like cost, design, analysis, manufacturing, and quality. And so we go through each of these stages really to find the right material for the right form, taking into a lot of the considerations that I talked about previously. A big part of composite materials, as I mentioned before, is the overall cost. And so that's one of the downfalls of composites. And you can see here, when we talk about the cost of using composite, the material cost only makes up about 25% of the total part cost. The customer has a lot of other costs that aren't always reflected by just the material cost. And so these are things like labor cost, processing cost, material handling, quality, and inspection. And so us as a material supplier are trying to develop and innovate ways to reduce that for our customers that brings down the overall cost of a composite part. And so these are things like engineered textiles, it's things like out of autoclave technology. So the capital investment for our customers is significantly less. It's also looking at fast cure and thermoplastic systems, which have a shorter processing time, so it means higher throughput for our customers. Part fabrication. So again, this is kind of tied to the last slide that I talked about. So why is the processing so expensive? Well, you have to go through all these different steps. And so when our customers receive the material, they have to store it at cold temperatures. This is for a thermoset. They have to go through the cutting and kitting stage, where you basically unroll the material, cut it into different forms and geometries. You lay that up into your composite panel. You then cure it, and then you cut it, you inspect it, and then you assemble it by combining with other parts. And so at the end of the day, time is money. And so all of these steps take time. And so what we try to do also is develop technology to help automate these, or help so the material itself is not the time limiting step. And so the yellow boxes just show where we have, and other people too, are developing technology to try to automate and basically make these steps less labor intensive, and also less costly for customers and part manufacturers. Automation is something that could significantly help with the cost if it makes sense. So when does automation fit? Hand layup is probably the most common form still used today, but it's by far the most labor intensive. And so the cost of this of a manual process it can be quite high. And so it can still make sense sometimes if the number of parts is small, if the labor rate is low, and if the part size is fairly small. Otherwise, it starts to become more cost effective and smarter to use things like automated processes. So on the bottom here, I'm just showing automated tape laying. If you can have something that's fairly flat, if you have something that doesn't have much contour, then these automated processes can significantly reduce the labor cost. It does change the material form, and so as a material supplier, we do try to tend to work with our customers to say, what is the geometry, what is the overall manufacturing form that you have, and then generally composite material, prepreg or impregnated form is then decided upon and then provided to the customer based to match their manufacturing process. For part fabrication, I see we're getting kind of close to the top of the hour, so I'm not going to spend too much time on these, but we can use simulation to help with some of the manufacturing, some of the downstream manufacturing. And again, this is where we kind of work together with customers to try to define the best material for their function. And so if you look at more complex shapes, it's not always as easy and obvious of laying up a flat panel. And so, the geometries that these prepregs have to take to still get the balanced layup or to still direct the fiber in the load direction can be kind of complex. And so we can use simulation to basically take the 3D geometry. We can then take a prepreg structure, which you see in the middle, and identify the most efficient way to cut out the different geometries that we have to lay up so we have the right fiber angle without minimizing or without wasting material, which then can be laid up to conform to these three-dimensional parts. And then finally, we take that information and then we go and can send it to an automated system to cut out the geometries. And so this again is just ways that we as a material supplier can help the downstream manufacturing of the composite material to reduce cost. When we look at new markets, aerospace is primarily where composites have had a foothold. We're talking about high performance but high cycle times. Automotive is where everybody wants to get to, but the challenge with automotive is the cycle times, the number of parts that you have to make in a given time. And so we go from aircraft, which are a handful per month, to automotive, to cars, which are tens of thousands of vehicles a month. And so the cycle time has to go up significantly. And so this has always been a challenge. We, as well as some of our other composite material manufacturers, are looking at reducing the cycle time significantly, but that's still one of the biggest challenges in automotive. And more recently, some new challenges have emerged. So things like, AAM, drones, aerial mobility vehicles, things like that. Actually, it's kind of combining both worlds. And so here we still have a high rate of crafts being generated, so thousands a month, but because they fly, they still need aerospace performance. And so this is just showing some of the new challenges that we have with composite materials going forward and some of the things that we can do to try to anticipate that and provide people with the right materials that they need to make composite structures. This is then just showing, what are some of the other innovations to anticipate, some of these new markets that are coming up and using composite materials. We have things like battery enclosures, and so I talked about before, electrification is a big area going forward. And so, things like fire-resistant materials, fire-resistant, battery casings, structural components are becoming really important to enable these types of materials. And so that's one. And then things like, using virtual engineering, part prototyping, testing. So, virtual engineering in general, where we can use, computation to predict the behavior, study different designs and structures to automate it and optimize it without going through the trouble and the cost of developing real-world prototypes. This is the last slide, and it's just showing, other key composite areas and applications. So, in addition to some that I talked about, aerospace and defense is a big area for composite materials. And also, satellites, antennas, rockets, and so space is an area where composite materials find a lot of application. Really anywhere now where you want high performance with low weight, composites are finding applications and the market continues to grow. And so I realize we're getting close to the top of the hour. That's the last slide I have today. Thank you everybody for listening. And I realize we don't have much time, but happy to take and field any questions that anyone might have.
Thank you so much, Matthew, for this excellent presentation and overview. I thought it was very educational, particularly for the students, just overviewing all different aspects of carbon fiber reinforced composites. So thank you for the wonderful lecture. We have a few questions, or a couple of questions already, and just a few minutes left in the hour. So actually, the first question is related to your previous slide. How does 3D printing of carbon fiber fit into your models or affect strength or cost?
Yeah, 3D printing is a bit of a challenge. We find that the product form of the actual fiber itself needs to be different than we typically use. And so a lot of times you're looking at lower fiber count. So things like 1K, 3K, it's hard to handle like a 50K, which we would use for impregnation. And so that's one. And then, yeah, a lot of the kind of fiber distortion, I would call it, can sometimes be higher with the 3D printing. And so we don't necessarily get the same kind of consistency as we'll see with traditional processing. But it is an area that's growing, and I think an area that we need to understand better. And so I think, some of our models right now struggle a little bit getting that fiber variation that we see with 3D printing, if we're talking about continuous fiber 3D printing. But it is an area that we're trying to investigate more and more.
Excellent. Excellent. We have another comment and question from actually my co-host, Ph.D. GTMI actually does host the NSF-funded Industry University Cooperative Research Center, IUCRC, for composite and hybrid material joining and repair. So that was just a comment that she made, and also thanks for a great lecture. Her question was, what do you see as the greatest challenges related to composite repairability and sustainability and recyclability?
Yeah, I mean that's a long answer with a couple different areas to talk about. Yeah, I think the repair side is challenging because thermosets make up the biggest majority of the materials used, and once you kind of set the shape, it's really hard to repair and get things to bond to it. So not that you can't, but I think that's one of the big challenges with thermosets is kind of when the chemistry is done happening, it's done, right? It doesn't want to have anything else bond to it. So I think that's where thermoplastics can be exciting. The repairability, the ability to kind of melt and reform and reshape, I think have a lot of promise. And then I'll just kind of dovetail that onto the sustainability and recyclability where, a lot of times, again, thermoplastics seem to have a lot of promise in that area where it's a lot easier to separate the fiber from the resin. With thermoplastics, we can also break down the resin easier into kind of its individual constituents and use it again. And so there's some inherent challenges with thermoset chemistries, but I think for both, bonding repair and kind of sustainability, recyclability, thermoplastics seem to offer a promising advantage there.
Thank you. I mean, that's a great answer, particularly coming from materials perspective. I think probably some of your customers could maybe address, more of the kind of the repairability part as far as like a scarf repair and that type of thing, those things that happen after the part is manufactured.
Yep.
Excellent. I had a quick question, and it's related to manufacturing as well, but for like automated fiber layup or automated tape layups, those type of automated processes to work with sort of some of the unidirectional fabric forms, does that help to reduce the labor? And I mean, is that sort of taking over that manual labor process when it comes to manufacturing, or what are some of the advantages, disadvantages of that?
Yeah, it depends on kind of the geometry of the part as well. If you have a lot of kind of complex, internal kind of corners, sometimes the automated processes just don't really work well for that. And so if the geometry allows for it, then yeah, you can save a lot of labor and time by going through the automated process. But again, it kind of depends on the geometry that you have. And then also it is going to be more capital intensive up front. And so, some of these ATL heads, these tape laying heads can be pretty expensive. So it depends on kind of the size of the part manufacturer and whether they can accommodate that initial capital investment. But those are probably the two main considerations. But if you can use it, then yeah, it can significantly reduce time and labor.
Excellent, excellent. All right, thank you so much, Matthew. It looks like we're at the end of the hour, but this was a fantastic presentation. As I mentioned, really just covered a lot of ground as far as the fundamentals, really, of carbon fiber reinforced composites. And I just want to thank you and for your time and for sharing with us this presentation. Hopefully, if we have your permission, we'll be able to share this on a link on our website, so that those who may have missed the presentation can view it later. And as a reminder, we do have another session next week. We have 2 more lunch and learn sessions to wrap up our series. And so next week we'll have Ebo Matthews, who leads the material science division of the Physical and Life Sciences Directorate over at Lawrence Livermore National Laboratory. And he will talk about enhancing process control in metal 3D printing. So, yes, okay, I was just looking at one comment that was made here. Yes, we will make it available as long as we have permission from the speaker. Okay, so thank you everybody for attending, and again, please join us next week. And thanks again, Matthew and the audience, and everybody have a great Monday.
Bye, everybody. Thank you.
You're welcome.